Welcome to this video on the phasor. This is part of a series of videos on circuit analysis in the frequency domain. Phasor is a complex number that carries the amplitude and phase angle information of a sinusoidal function. It is rooted in the Euler's identity. Based on the Euler's identity, we can write that cosine of theta is the real part of e to the j theta and that sine of theta is the imaginary part of e to the j theta. For a sinusoidal voltage source Vm cosine of omega t plus phi, we can write that the cosine of omega t plus phi is the real part of e to the j omega t plus phi. Vm e to the j phi is the phasor representation of this sinusoidal source. It is a phasor because it carries the amplitude and phase angle information of this sinusoidal source. Because phasor is a complex number, it can be represented in rectangular form as well. We can define a phasor transform that, given a sinusoidal function, returns its phasor representation. Note that phasor quantities are represented in uppercase. Using the phasor transform, the sinusoidal function can be transformed from the time domain to the complex number domain. From the phasor representation, it is possible to go to the time domain representation using the inverse phasor transform. As you can see, to obtain the time domain expression, we multiply the phasor by e to the j omega t and then take the real part. Note that the actual value of omega cannot be obtained from the phasor representation because the phasor representation contains only the amplitude and phase angle. The phasor is widely used in circuit analysis because it allows to obtain the amplitude and phase angle of the sinusoidal steady-state response using the algebra of complex numbers rather than having to solve differential equations. In a linear circuit driven by sinusoidal source, the steady-state response is also sinusoidal with the same frequency. The general form of the steady-state response is the real part of A times e to the j beta times e to the j omega t. A is the amplitude of the response and beta is the phase angle of the response. For the circuit whose response was derived by solving the differential equation resulting from applying Kirchhoff's voltage law, let's postulate that the steady-state solution for the current has amplitude Im and phase beta. We apply Kirchhoff's voltage law and replace the sinusoidal voltage and current with the real part of their corresponding phasor multiplied by e to the j omega t. Note that differentiation and multiplication by a constant can be taken inside the real part operation. In addition, note that the sum of real parts of two complex numbers is the same as the real part of the sum of the two complex numbers. If we choose to use the sine function instead of cosine for the sinusoidal source and the sinusoidal response, we start over and use the imaginary part operation. When both the real parts and imaginary parts of two complex quantities are equal, the complex quantities themselves are equal. We can now find expressions for Im and beta. Comparing these expressions with those obtained by solving the differential equation, we can see that the same result has been obtained without having to solve any differential equation. The Phasor transform is widely used in circuit analysis. As we have seen, circuit analysis involves adding currents and voltages. For this reason, it is important to know what the corresponding phasor is when sinusoidal quantities are added. When a sinusoidal entity is the sum of a number of constituent sinusoidal components, all having the same frequency, the phasor representation is the sum of the phasors of the individual terms. In this first example, a sinusoidal current with amplitude of 10 and phase angle of 20 degrees is expressed using a sine function. It is requested to find the phasor representation of this current. In the second example, a sinusoidal current is given as the sum of two cosines each having a different amplitude and phase, but the same frequency for both cosines. It is requested to find the phasor representation of this current. If the problem had asked to represent the sum of the two cosines as a single cosine, we represent the phasor that we just obtained in the time domain. In the third example, a phasor current is represented as the difference of two phasors. It is requested to find the time domain representation.